those of you who are new, you are watching Quantum ASMR. And for those of you who aren't new, welcome back. Welcome back. So, today's video, today, we are going to be talking a little bit about rocket science. Rocket science, yeah. So I did a video on this like 4 years ago. I think it was like the third or fourth video I did. Yeah. And I don't know, I just thought it would be fun to bring it back and to get myself back into the science and math game. So we're gonna talk rocket science today. So, we know that rockets shoot off into space. They can orbit the Earth, they can fly to the moon, they can travel through space, right? But how exactly do they do that? How do they fly? Well, we know that rockets have fuel or propellant to blast themselves off into space and to get them going through space, but how exactly does that work? And then that also leaves the question, well, space is like a vacuum, there's no air, right? But what about in a situation where it's being pulled by the Earth? How is it able to escape the Earth? Well, we will talk about those two questions today. So the first question is, how do they move to begin with? Well, rockets use what is called thrust. By expelling part of its mass. So basically like expelling part of itself with high velocity. So that's where the fuel comes in. It expels the fuel to thrust itself, right? Now, this is done and was figured out through the law of conservation of momentum. Newton's law of conservation of momentum. So what is the conservation of momentum again? So in a closed system, so in a system by itself, the total momentum of that system remains the same. So it stays constant within that closed system of itself. Okay? So in order to get into understanding how this works, we need to get a little bit into math, the mathy stuff. Before we get into the math, we need to draw some diagrams just to kind of explain how this works. So, I used my little pencil and microphone. If you guys follow me on Instagram, you saw that I tried it out already with a reel that I posted, but I attached the microphone to my pencil. I just used a regular one instead of a mechanical one because I thought it would make like a little bit of a scratchier sound, and I think I was right. So we're going to be using pencil and paper to explain the mathy parts, and then we'll get back. So today we are going to be talking about the Silkowski rocket equation. The Silkowski rocket equation, also known themselves by expelling mass from themselves at high velocity, at a high velocity, at a high velocity. So let's look at two different diagrams to demonstrate what's going on. So number one, this is when time is 0, so t equals 0. We have the rocket with its fuel still inside of it. So I've labeled the rocket itself M, and then the fuel delta M, which is that little box of stuff, and you'll see why it looks the way it does in a minute. And this rocket and fuel together is moving at a certain velocity. We don't know what it is. We're going to be using just general stuff, so we're not putting any numbers into this. So it's moving at a certain velocity, and this whole system right now has a momentum of, we're going to call it P1. It has a momentum of P1. This whole system. Okay, so the next thing we're going to look at, number 2, is when t equals delta t. So a certain time has passed now. And what's going to happen to the rocket fuel system is that the rocket, the M, is now expelled the delta M. So you can see it pointing away. From the rocket itself. So delta M is going one direction and M is going another. Now this gives the rocket itself M a velocity of V plus delta V. V plus delta V. And delta M, the fuel, is expelled and moving in the opposite direction at some other velocity, which we call the effective exhaust velocity. So it's moving at the effective exhaust velocity, which I'll do V sub EF for that one. And this whole system itself has a momentum. This entire system has a momentum of P2. P2. Alright. So now that we have those two diagrams, let's get into the math portion. So we're going to start with this equation. The sum of the external forces is equal to the limit as delta t approaches 0 of P2 minus P1 over delta t. And while we're at this, let's just remind ourselves that P, the momentum P, is equal to mv, mass times velocity. So since P is equal to mass times velocity, now let's take those P1 and P2 momentums and kind of lay them out, okay? So looking at P1, we are looking at that whole system in number 1, the first diagram, looking at that whole system. Okay, so we've got a mass of m plus delta m plus delta m, and then we've got a velocity v. So P1 is equal to m plus delta m in parentheses times v. Alright, now we have P2, and P2 is a little bit trickier, but not too bad. So we efficient exhaust velocity now, and for P2 we now have m times v plus delta v plus delta m times v minus the efficient exhaust velocity. Okay, so now we are going to look at our original equation. The sum of the external forces is equal to the limit as delta t approaches 0 of P2 minus P1 over delta t. So we're going to look at P2 minus P1. We're going to do that right now, substituting in what we just wrote for P1 and P2. So that ends up being, and also I'm going to distribute, right? We know the distribution property. So distributing that and then doing the subtraction, we end up with mv plus m times delta v plus delta m times v minus delta m times v ef. And then minus m times v minus delta m times v. And we've got two things that can cancel out right now. We've got mv and we've got delta mv that are canceled. And so we're left with P2 minus P1 equals m times delta v minus delta m times the efficient exhaust velocity. Okay, so now that we have P2 minus P1, we're going to redefine some terms. So first we're going to look at that minus delta m, that negative delta m. So this guy, because a couple of things, we've got a loss in mass of the rocket, right? Because the delta m, the fuel's gone. But because of that, we're moving even more in the direction of the original velocity. And also because mass itself is not negative, we are going to change the negative delta m to just dm. And also we have a delta v. We're going to change that to dv. We are going to change that to dv. And then finally delta t. We are going to change that to dt. Change that to dt. So then the sum of the external forces would end up being m times dv over dt plus the effective exhaust velocity times dm over dt. Because remember, the original equation that was the P2 minus P1 over delta t. Okay, so now that we've got this redefined equation, we have to remember that the sum of the external forces is equal to 0. There are no external forces acting on the system, so it's equal to 0. So what we're going to do now is we're going to bring that effective velocity times dm over dt, we're going to bring it around to the other side of the equal sign. So now we have m times dv over dt is equal to negative effective exhaust velocity times dm over dt. And now that we have dt on both sides, we can just cancel them out because they cancel each other out. first side, we've got the integral of dv, and we have to place our boundaries. So we're going to start with v. So it starts at v and then goes up to v plus delta v, v plus delta v. So the integral from v to v plus delta v of dv is equal to, and then the next one is going to be the integral from the initial mass to the final mass of the negative effective exhaust velocity over m dm. So then we just integrate. So the first side ends up being v plus delta v minus v. So the two v's cancel out and we're left with just delta v. So delta v equals. And then this one was a little trickier, but if you know your integrals, you'll be able to do it. And it ends up being the negative effective exhaust velocity times the natural log of the final mass over the initial mass. Or we could switch that over to get rid of that negative sign, and it ends up being the positive effective exhaust velocity times the natural log of the initial mass over the final mass. So the end equation we have now is delta V is equal to the effective exhaust velocity times the natural log of the initial mass over the final mass. And that, my friends, is the ideal rocket equation. The ideal rocket equation. Okay, so now we know, based on the ideal rocket equation, how this whole blast off is supposed to work, how this thrust works for the rocket to move itself forward in space. And the next question would be, okay, well, it can move itself forward in space, but what about when it's on Earth? How does it even get up into space? Like, how does it blast itself off into space? Well, we can again use the ideal rocket equation. Ideal rocket equation. In order to figure this out, we need to remember a few things, okay? So, first of all, it is possible to escape the Earth by a certain velocity, which is called the escape velocity, and that basically means how fast you have to be going up through, like, the Earth's atmosphere, how fast you have to be going away from the Earth in order to escape its gravitational pull. And again, that is called the escape velocity, which I believe for the Earth is 11.2 kilometers per second. 11.2 kilometers per second. And one thing to note is that this escape velocity would be the same for any object. So as long as it's on Earth, different planets have different escape velocities for them, but for Earth specifically, 11.2 kilometers per second would be needed whether a pebble wants to escape or whether I want to escape, or, you know, whether a rocket wants to escape. It's 11.2 kilometers per second. Okay, so now that we know that, we know that the change in velocity starting from ground to going up has to be the escape velocity. So our change in velocity now is 11.2 kilometers per second. So we know the escape velocity is the change in velocity. So 11.2 kilometers per second. If we have the velocity at which the propellant expels. So remember, the propellant has to expel at a high velocity, right, in order to work. So if we know the velocity at which that's leaving the rocket, and we know the mass of the rocket without the propellant in it, without the fuel, then we can figure out how much fuel we need to blast this rocket into space, okay? And again, we can just use the ideal rocket equation for that. So looking at our terms, we've got the effective exhaust velocity, we've got the initial mass, and we've got the final mass. Okay, so we already know what change in velocity and effective exhaust velocity is. So we're going to look at the initial and final mass. So in this case, the final mass would just be the mass of the rocket without any fuel. So if we were only using enough fuel to shoot it off into space, we would be left with just the mass of the rocket, no fuel, no propellant in it. That means that the initial mass is the mass of both the rocket and the amount of fuel it takes to get that rocket to reach escape velocity. Okay, so what we want to find out then, if we already know the mass of the rocket, what we want to find out is the amount of fuel, or the mass of the fuel needed. So we could just rearrange that ideal rocket equation to just get the initial mass on one side by itself. Okay, so rearranging that, instead of logarithms now, we've got an exponential function. So it ends up being the initial mass is equal to the final mass times e to the escape velocity over the effective exhaust velocity. Okay, you with me? Okay, so now that we have that, we can figure out how much fuel is needed to send a rocket into space. Let's do an example. So say that we have a rocket, right, and its mass without fuel, without propellant, is 280,000 kilograms. 280,000 kilograms. And let's say that our effective exhaust velocity is 4.5 kilometers per second. 4.5 kilometers per second. 4.5 kilometers per second. I looked up the typical range of exhaust velocity, and I think it said between 2 and 4.5 kilometers per second. So we're going to use the high one, okay? So now that we have those two, and we also have the escape velocity from Earth, 11.2 kilometers per second, we just plug those into the equation, right? And solve for initial mass. So doing that gives us 3,373,407 kilograms. We're not going to do we're not going to do significant digits for this one because it's just an example. But that gives us over 3 million kilograms in mass, right? So in order to find the actual amount of fuel mass, we're going to have to subtract the mass of the rocket itself, right? So we'll just subtract 280,000 from that number, and we end up with 3,093,407 kilograms of fuel. That means that the rocket is only about 8.3% of the entire thing. So it takes over 90% of fuel just to blast this rocket into space. Now it might seem like really drastic, but that's actually how they work. A lot of the rocket just ends up being fuel. So now you know how a rocket can propel itself into space, and you also know how a rocket can shoot itself up into space from the Earth. And I think we're going to end it at that, guys. This was a lot of fun to do. There was just the new thing with the pencil and the microphone, but yeah, comment down below if you want to see anything else with science and math. Again, a lot of you asked me to do random stuff that is like above my level of expertise, so be gentle with me, but I'll be happy to do a lot of other things. I still want to do the double slit experiment. I still have to get the stuff for that because I want to do it properly, guys. But anyway, comment down below what else you want to see from me. And if you like this video, please give it a thumbs up. Give it a thumbs up. And yeah, comment that you liked it too. Everything helps, just so you know, guys. But with that being said, we're gonna end the video. So I hope that you have a good night. A good night. Or a good morning. A good morning. Or a good day. Whatever time of day you're watching this, I hope you are doing very, very well. And I'll see you all